Okay, so as I promised, I want to talk about 2007 article, which is Locality Sensitive Discriminant Analysis, by people in Yahoo and Google, I think. So LDA fails. Linear discriminant analysis fails to discover local geometric structure. It's a good global. I mean, it cares about global structure, but doesn't care about local structure. So when data is not sufficient, local structure is generally more important than global. So nearby points with the same label should be close to each other, while nearby points with different labels should be far apart. And so in traditional linear discriminant analysis, what does it do? It cares about global statistics such as mean and covariance. But global statistics like mean and covariance, they fail when we don't have sufficient data. So first, we should construct a nearest neighbor graph to model the local geometrical structure of the underlying manifold. So our graph, we should split our graph to within class graph and between class graph. So we have given m data points. x1, this is a vector, x2, xm is inside Rn. And so we have xi, we have k different neighbors, xi1, xi2, xi3, xik. You have k nearest neighbor, and you can do it in Python very quickly. And so Wij is a very sparse matrix. I've done all of them in Python, and W is sparse. You can use SciPy to work with those sparse matrices. And if xi is in neighbor of xj, or xj is in neighbor of xi, it is 1. Otherwise it is 0. I mean, it fails to discover discriminant structure. It may fail, but it's very. You can use other weights as well. You can use, for example, the Gaussian kernel or something like that. But I mean, the authors of this article use the most simplest way to define your weights. So we make two graphs, G within graph and G between graph. And L of xi is a class label of xi. And we define neighbor xi, neighbor within of xi, to be all points, as I said, that the labels of them are equal. Label of any 2 points is equal. And J is between 1 and the k's neighbor. And you have a nearest neighbor between class of point xi. Again, it's like xi, xj, but this time our labels are different. So our label is different for the next point. And j is between 1 and the case neighbor. And so we define WBIJ between class as, so I've separated, unlike my previous page that I showed, we have one WIJ and it fails to discover discriminant structure. Now WBIJ and W within IJ are separated. So I care about the discriminant structure. And if xi is in neighbor of within of xj, or xj is in neighbor within of xi, is 1, otherwise is 0. The same for between. So xi is neighbor of between xj, or xj is neighbor between xi, is 1, otherwise is 0. So you know that weight is equal to W between and W within. And connected points of GW stay as close as possible. What do I mean? It means that I should minimize yi minus, y is the transform, in the transform or in the embedded space, squared wij within. And so this one says that connected points of GW, of G between, graph within, stay as close as possible. And we have another constraint as well. Connected points of your graph stay as distant as possible if it is between. So I also want to maximize yi minus yj squared WB between ij. So both of them we want to care about. So it's a bi-objective optimization problem. You can see it as a multi-objective optimization and use scalarization, or you have many different paradigms in the multi-objective. But traditionally, they put it under Rayleigh quotient, and so it's a ratio, and they solve it very quickly. They don't care about your Pareto set and those things. I don't know why machine learning community does not like to talk about multi-objective optimization, and just those they do very naive and simple single scalarization, and so strange. But multi-objective, some problems are intrinsically multi-objective, and you lose a lot of information if you don't formulate it as a multi-objective optimization. Anyway, let's just do y transpose is 8x. X is your data, n by m, and a is your transformation, which is n is dimension. You know, you have, for example, in my case, it was 7,070, I don't remember, pixels. So this was my dimension in my article. And y transpose is 1 by m. M is sample size. So you have m samples. So now y transpose is 1 by m, and so you project your data, which is n-dimensional, to just one dimension, because it's just 1D, one dimension. You project in very high dimension to just one dimension, which is y. And so if you just write minimize, let's do it in the next page. If we just substitute that transformation, so A is a projection vector, yi minus yj squared w within ij, which is equal to 1 over 2 A transpose xi minus A transpose xj squared w weight ij. So it's very interesting. If you just work on this, a Laplacian automatically shows up. So it's not, you have not created, it is, you have not inspired it from physics. It is just, if you just work on this, you see that this is equal to A transpose xi. This is your diagonal matrix within II, xi transpose A minus A transpose xi within ij xj transpose A, and so this one is set to 0. We set it to 0, and we will notice that this term is exactly y transpose dwy. But if this dw becomes large, it means that high density around xi, and we don't like it. Okay, so this one is equal to A transpose x. The sum is equal to A transpose x dw x transpose A, and for the so this one we put it constraint equal to 1, because I told you that if this d becomes large, you have high density around xi, and we don't like it. So we put constraint and say this is just 1. Minus A transpose x w within x transpose A, and this is equal to A transpose x Laplacian within x transpose A. So this Laplacian is again diagonal minus your weight. And so your constraint is this one. Put this equal to 1. In other words, your constraint is y transpose dw1 is equal to 1. So finally, you can say that you want to minimize 1 minus A transpose x w x transpose A. And so 1 is just constant, so we don't care. Minimize of a minus things is like saying we want to maximize, and the rest of that is A transpose x w x transpose A. So this is the first minimization that we wanted to do. It is for within classes. Now let's talk about between classes. So I said we have another optimization. We want to maximize between. So yi minus yj wbij. So everything is the same, is equal to, but this is just between. So this is equal to 1 over 2 ij. We just substitute our projection. It becomes bij, and this is A transpose x db minus wb x transpose A transpose x Laplacian of between x transpose A. So again, Laplacian of between is diagonal between minus weights between. So finally, we want to maximize over A of A transpose X, Laplacian X transpose A. And so this is our second optimization problem. So if you just combine the first one and the second optimization, so totally we want to arg maximum of A transpose X and use a simple scalarization. Alpha is between 0 and 1, so alpha LB plus 1 minus alpha within X transpose A. And don't forget you're subject to A transpose X, dW X transpose is equal to 1. And the solution, put your Lagrangian multiplier for this one, and if you solve this like any other method in machine learning, your solution is maximum eigenvalue. So your solution of this problem is maximum eigenvalue solution to the generalized eigenvalue problem. So your generalized eigenvalue problem is 1 minus alpha W within X transpose A is equal to lambda X D within X transpose A. So lambda 1 is greater than lambda D. And so you get your matrix, putting all of those A, because each of them, you have a different eigenvalue, and you sort them, and you sort the eigenvectors as well. So you have A1, A2, AD, and don't forget that your projection is n by d, and so your projection can be written as A transpose xi. So this is your final projection, and you get A. And so you see everything is related to generalized eigenvalue problem. So in the next lecture, I will talk about generalized eigenvalue problem, and I will talk about what is a pencil, what is a matrix pencil, and how I solve generalized eigenvalue problem. Traditionally, you solve it by QZ algorithm, which is a generalized kind of shared decomposition, but I don't recommend that. We have much better, faster methods, much more scalable, more importantly, much more scalable methods. And because gradient methods are very nice. I prefer them. I can say I prefer them over Newton type methods because they are second type. They need your Hessian. Getting Hessian is interesting, but if you are doing it, if you just need successive convex approximation to come up with your special non-convex problem, then it is okay. I use Hessian and I like to use it. But if you just want to do a simple convex optimization, so it's very easily and more scalable to do it with gradient first order methods. And anybody know the fact that Newton type methods are not faster than gradient methods, unless you use some kind of block coordinate methods, coordinate gradient descent, coordinate ascent methods, and those type of algorithms which are blockwise. Otherwise, it is not fast, and we can prefer first order methods. I mean, there are many advanced first order methods. I mean, proximal methods and more generally mirror descent methods, which is really nice because it could be skewed if you put it, if it is not ID, then it can become, it can have some skewness along some directions. So mirror gradient descent is very general. You combine it with ideas like proximal gradient methods, and you can come up with many problems in non-Ethmos optimization problem, and so in the next lectures I will talk about generalized eigenvalue problem. I will talk about sparse generalized eigenvalue problem, but I use a smooth optimization problem. And I show you how I use majorization minimization to tackle the sparsity of the generalized eigenvalue problem, because your motivation could be anything. You may have seen sparse PCA, you may have seen lasso, so many of those ideas that care about L1 norm, but in the next lectures I want to talk about sparse generalized eigenvalue problem, but I care about L0 norm, not L1 norm. So for example, in lasso you care about L1 norm, but in the next lectures I only talk about L0 norm. And it is very discontinuous. First I approximate it with a continuous, and then although it is still not convex, so I try to use majorization minimizations for this purpose.